Hey everyone, my name is Saumitra Sapre, and this is a demo lesson for my TA application at UC San Diego. In this lesson, we shall learn how to detect loops in a linked list. At this stage, I am going to assume you all know what a linked list is as a data structure and how to code it. This is a normal linked list without a loop. We can see that the head pointer points towards the first node and the last node terminates in a null pointer. This is a terminating condition that we use while traversing the linked list, wherein we check whether our temp pointer has reached the null pointer or not. Now this is a linked list which indeed contains a loop. We can see that the last node does not terminate in a null pointer, but instead points towards the second node. If we try to traverse this linked list, we can see that we shall end up in an infinite loop because the condition of arriving at the null pointer shall never arrive. We shall go from node 1 to 2 to 3 to 4 and back to 2 again, and this cycle shall continue indefinitely. So as a rule of thumb, we can remember that a linked list with a loop is a linked list which doesn't terminate at all during its traversal. In this lesson, we shall learn two algorithms which shall be used for detecting loops in a linked list. The first algorithm is a pretty simple algorithm called as hashing. In this algorithm, we traverse the linked list normally, and while traversing, we also store all the visited nodes in a special data structure called as the hash table. If at any stage during the traversal we reach the null pointer, then it means that the loop does not exist in the linked list. However, if we encounter a node that we have already visited, then that implies that the loop exists in a linked list. Let us see this algorithm in action. Here we have a simple linear linked list which doesn't contain a loop. We start from the first node and check whether this node exists in our hash table or not. And if not, we add this node to our hash table. Then we move ahead. We then arrive at the second node, check whether this node exists in our hash table or not. If not, we add it to our hash table and continue. We do the same with the third node, the fourth node, the fifth node, and at this stage we can see that we have arrived at the null pointer, and at no stage during this traversal we have visited a node that we have already encountered. So according to the hashing algorithm, we can conclude that this linked list doesn't contain a loop. Now let us apply this algorithm to a linked list which does contain a loop. As always, we start from the first node. We check whether this node exists in our hash table or not. And if not, we add it to our hash table. And we move ahead. We then check if the second node exists in our hash table or not. If not, we add it to our hash table and we move ahead. We do the same with the third node, the fourth node, the fifth node, the sixth node. And at this stage, we can see if we move ahead, we have arrived at a node that we have already visited, that its entry already exists in the hash table. So according to the algorithm, we conclude that this linked list indeed contains a loop, which is true. We can see that the linked list contains a loop. Now let us analyze this algorithm a bit further. We can see that the time required for this algorithm to complete is directly proportional to the length of the linked list. That is, the more the nodes the linked list contains, the more time this algorithm will require to complete. So we can say that the time complexity of this algorithm is of the order of n, and we denote it by big O of n. We can also see that we require an additional auxiliary data structure to store the visited nodes. And if the size of the linked list is more, we shall require more auxiliary space to store the visited nodes. So we can also say that the space required for this algorithm is also directly proportional to the length of the linked list. And we can say that the space complexity of this algorithm is of the order of n. And we also denote this by big O of n. Now there is another algorithm which improves on the space complexity aspect of this algorithm. And this algorithm is called as Floyd's cycle finding algorithm. This is also a very simple algorithm where we start with two pointers, fast and slow, both of them which are initialized at head. We traverse this linked list normally, but with a slight change. We move the slow pointer by 1 unit and the fast pointer by 2 units until either of them reach the null pointer. If at any stage during this traversal the slow pointer is equal to the fast pointer, that is, the slow pointer and fast pointer have reached the same node, then we conclude that this linked list contains a loop. Otherwise, we conclude that this linked list doesn't contain a loop. Now let us see this algorithm in action. Here we have a linked list which contains a loop. We initialize the slow and fast pointers at the first node or at the head node. we move the slow pointer by 1 unit and the fast pointer by 2 units. So the slow pointer arrives at node 2 and the fast pointer arrives at node 3. In the next iteration, slow pointer arrives at node 3 and fast pointer arrives at node 5. In the next iteration, S arrives at 4, F arrives at 7. Then S arrives at 5, F arrives at 9. Then S arrives at 6, F arrives at 5. Then S arrives at 7 and F also arrives at 7. At this stage, we can see that the slow as well as fast pointers have reached the same node, that is S is equal to F. And according to the Floyd's algorithm, we conclude that this linked list contains a loop, which is also true because we can see that this linked list contains a loop. Now let us apply this algorithm to a linked list which doesn't contain a loop. We initialize the slow and fast pointers at the head node. We move the slow pointer by 1 unit and the fast pointer by 2 units. So the slow pointer arrives at node 3 and fast pointer arrives at slow pointer arrives at node 2 and fast pointer arrives at node 3. At the next iteration, S arrives at 3, F arrives at 5. Then S arrives at 4 and F arrives at the null pointer. Because the fast pointer arrives at the null pointer, and at no stage during this traversal was the slow pointer equal to the fast pointer. So we conclude that this linked list doesn't contain a loop, which is true. We can see that this is a simple basic linear linked list and it doesn't contain a loop. Now let us analyze this algorithm a bit further. We can also see that for this algorithm, if the length of the linked list increases, the time required for this algorithm to complete will also increase. So the time required for this algorithm is directly proportional to the length of the linked list. In other words, we can say that the time complexity of this algorithm is of the order of n, which we denote by big O of n. However, the space required for this algorithm is constant. We do not require an auxiliary data structure to store the nodes, as we did in the hashing algorithm. So the space required for this algorithm to complete is constant, and we denote this by big O of 1. Now, how does Floyd's algorithm actually work? The working of Floyd's algorithm is based on two basic facts. First, when the slow pointer enters the loop, the fast pointer is already inside the loop. This is quite intuitive to imagine because we move the fast pointer by 2 units and the slow pointer by 1 unit. So the fast pointer will always be ahead of the slow pointer. The second fact is that the distance between the slow and fast pointers will always increase by 1 after every iteration. This might not be as intuitive to imagine, so let us look at this in action. We have a linked list where the slow pointer has just entered the loop and the fast pointer is ahead of the slow pointer by 2 units. So the distance between the slow and fast pointer is equal to 2. In the next iteration, S will reach here and F will reach here. And at this stage, the distance between the slow and fast pointers is equal to 3 units. We can see that the distance between the two pointers has indeed increased by 1 in one iteration. In the next iteration, S shall arrive here and F shall arrive here. And the distance between the slow and fast pointers is equal to 4 units. We can again see that the distance has increased by 1 unit in one iteration. In the next iteration, S shall arrive here and F shall arrive here. And the distance between the slow and fast pointers is equal to 5 units. But because these nodes are arranged in the form of a loop, the distance between them is also equal to 0. Now what does this imply? This implies that there will always arrive a point where the distance between the slow and fast pointers is equal to the length of the loop. And if the nodes in the linked list are indeed arranged in the form of a loop, then this is the stage where the slow and fast pointers will always meet. So this is the crux of the Floyd's algorithm. Now at this point, many of you might wonder, what if the fast pointer skips over the slow pointer? And is this condition even possible? Now for the sake of hypothesis, let us assume that this is indeed true. Let us assume that the fast pointer has indeed skipped over the slow pointer. So our fast pointer is at node j plus 1 and the slow pointer is at node j. Now let us rewind back time and see where the fast and slow pointers were in the previous iteration. Because we increment the fast pointers by 2, in the previous iteration, the fast pointer would be at j plus 1 minus 2th node, which means that it would be at j minus 1th node. On similar lines, because we increment the slow pointer by 1, in the previous iteration, the slow pointer would also be at j minus 1th node. And according to our algorithm, we would have already terminated our traversal when this condition is true. which means that the condition where the fast pointer skips over the slow pointer shall never arrive because we would have terminated our algorithm long back. So this is never possible. The fast pointer and slow pointers shall always move in sync, and the fast pointer shall never skip over the slow pointer. Let us see a sample code for this algorithm. I have written a simple function called as detect loop, which returns a Boolean value. We have the two pointers slow and fast, which are initially initialized at head. Now I have written a while loop, which terminates when either the slow, the fast, or the next node of the fast pointer is equal to null. I increment the slow pointer by 1 unit and fast pointer by 2 units. And if at any stage during this traversal the slow pointer is equal to the fast pointer, I return true. Otherwise, I return false. Now, I have written two simple linked lists. One of them contains a loop and the other doesn't. And let us run this function over these two linked lists. We can see that the code has finished its execution. And for the linked list which contains a loop, the function has terminated with a true condition. That is, the loop exists, which is true. And for the linked list which doesn't contain a loop, the function has terminated with a false condition. That is, the loop does not exist. We can see that the Floyd's algorithm indeed works for detecting a loop within a linked list. And that is the end of this lecture. I hope that you have all understood this and it is clear. Thank you all for listening to me and have a nice day.